Hello, hello! It's Wednesday, my dudes. Welcome to yet another pep talk. This time, I was even debating doing one. I'm just kind of tired. But I have about an hour and something long drive home, depending on traffic. And I don't think... I might spend the full time talking. I don't know. We'll see. You'll definitely know by the duration of this video. But today, I was trying to think, what can I talk about for like an hour without being pedantic or, repeating myself a ton? Or what's a topic that is broad enough that I can talk about for a long time, practical enough that it should be talked about for a long time, and ubiquitous or common enough that it needs to be talked about because it will apply to your daily life. It's funny, I'm rounding the parking garage right now, and I think on the last pep talk I said the word ubiquitous at the exact same point as last time when I rounded this corner. It just hit me like, I like that word, ubiquitous. It means something that is common. Just a fancy way of saying it. It makes me sound smart. But anyway, so today I wanted to talk about electricity and what it is. Because electricity powers our everyday life. Powers your body. I mentioned it previously, I think, in my sleep pep talk, and I've definitely mentioned electricity, I think, in my thermodynamics one, and I've mentioned it briefly in other things. But I haven't dedicated a full talk to it. And it's definitely a broad enough topic that has many facets to understand that I can try my best to boil down and make practical, and I will. So, yeah, electricity and what it is. Where to start? Well, let's start with what electricity is. Electricity is the flow of something. It's the flow of electrons. Electricity, electrons, elect. Don't ask me for Latin roots. I'm not sure. But electricity in its simplest form is the flow of electrons. Now, you might be asking yourself, hey, Daniel, you talked about the nature of matter at some point. I think I did. Matter is composed of neutrons, protons, and electrons. How can matter not have electrons comprising it? Well, it's not that the matter is destroyed or the energy is converted in any weird way. It's that electrons can flow from one atom to another. That's how you get ionic bonds. Covalent bonds, well, yeah, it's definitely how you get ionic bonds. I'm trying to figure that's how you get covalent bonds or something else. But ionic bonds deal with electronegativity, which is a measure of how much an atom of a particular element wants electrons. Like how hungry it is, how much does it thirst for electrons. That's electronegativity. And it's just a property of matter that you can measure. And scientists have measured, and if you look at a periodic table and they have it for electronegativity, you can see that. So some atoms and some metals and some things and matter really, really, really desires electrons, and others don't. And the reasons they do that is because they want to be stable. And to be stable is to have the least amount of energy as possible at any given time. So things with high electronegativity usually have valence shells that are almost full but aren't quite full. And a valence shell is just electrons orbit nuclei, atomic nuclei in set orbits, and those orbits have distinct shapes, and those are called valence shells. It's just how the electrons orbit, so don't get hung up on the jargon and the nomenclature. But valence shells come in pairs and come in sets, and it scales. There's SP, D, and F valence shells, and those are just different shapes. And you can look them up. They're pretty cool. And they're pretty complicated to model as well for some of the more complicated ones. F's and D's and F's are harder. But Yeah, valence shells, they want to be complete because that's when they are stable usually. And so some elements like anything close to the right side of the periodic table that's not a noble gas, it usually has a high electronegativity. That's like fluorine and stuff over there. Fluorine, I think, has the highest electronegativity of a 4.0, and then everything else is less than that. And then to have an ionic bond, which is what happens when something shares, or something steals an electron from something else, and then because they have a charge now, positive or negative, which I'll get into that in a bit, they are attracted to each other and then form a bond. Covalent bonds is when they share electrons. That's the difference between ionic and covalent. And you might be asking, well, what does this have to do with electricity? Well, I'm getting to that. So, electrons are how things are bonding to each other. And if they share it or if they steal it and then suddenly need each other to be whole again, difference between ionic and covalent bonds. Well, electricity is the flow of electrons. So if an ionic bond is stealing an electron from another atom and then pulling them together, then there's a flow of electricity, and an electron has moved from one atom to another, and that happens. So certain metals, certain atoms, certain materials are able to have their electrons stolen more easily, as well as have electrons flow through them more easily. And I could break down the periodic table and talk about that, but there's some stuff where electricity just doesn't like the flow. Those are your good insulators, is what they're called. So stuff like noble gases are good insulators, vacuums are pretty good at insulators. Anything that really has a full valence shell is a good insulator, or something that's kind of doesn't need much. Like I'm trying to think of an example, an actual metal, where metals are bad examples. I'm trying to think of an actual compound, like ceramics. Ceramics are pretty good insulators against electricity. And ceramics are usually made of silicon and oxygen, if I'm not mistaken. And those form very strong bonds that complete each other. So they don't need to share electrons out with other things. Like, they're pretty insulative. They don't need the flow to complete them, and they don't want to share their electrons because they're pretty tight already. They're close together. So that's why I brought in the bonds, because it'll help you understand how electricity flows and what electricity is. So, like I said, electricity, it's electrons. I just missed my exit, which means I gotta do a U-turn. That's gonna be fun. Can I do one of this light? Ooh. Yes, I can. Cool. I gotta flow in the opposite direction. Put it that way. Yeah, which electricity is cool. So let's talk about charge for a little bit, because I mentioned it with the ionic bonds, and electrons are negatively charged. Well, let me tell you, charge is an arbitrary thing that humans came up with and designated. So we say that protons are positive, electrons are negative, neutrons are neutral. They don't have a charge. And that is true as far as the standards we've set, but there's nothing in nature that says this is a positive or this is a negative. It's kind of arbitrary. Like, protons could have an electric or a negative charge, and electrons could have had a positive charge, and atoms still would have worked the same. In fact, they do. That's called antimatter, if you want to make it a little bit more absolute. But yeah. Okay, made the U-turn. Cool. But yeah, antimatter is just simply matter with opposite charges. So an antiproton is just a proton with a negative charge. So, the more you know. And, you know, when antimatter and matter come together, they release a crap ton of energy. But I digress on that. I'm not talking about antimatter reactors or anything. Although, good ways to generate electricity, for sure. I got a big truck next to me, and I need to get over. Very big truck. That truck has a battery in it that runs on electricity, which is that battery is storing electricity in a chemical process using bonds. That's why it's practical. This kind of stuff is practical. Now I'm getting kind of deep into the physics. So we talked about charge. Electrons have a negative charge. Negative things are attracted to positive things. Electricity flows. This is counterintuitive. Electricity flows from negative to positive. Now you always will see it written differently. You'll see it like when you see a symbol for a battery in a wiring diagram. It's always the positives on top, negatives on the bottom. Well, that's true. But it doesn't flow from positive to negative. It goes negative to positive because electrons. Well, actually, that's not true. Hold on. Electrons are negatively charged. The flow of electrons make something negative, but when they flow out of something, it makes that thing more positive because it's, you know, it's you're removing negative charge. Charges add, they're additional, they're summations. So I guess when you think of it that way, in some sense, it flows from positive to negative because the electrons are leaving the positive side and flowing back around to the negative side. So I guess, okay, so it does flow that way. Maybe I'm mistaken, but it's more of a semantics type thing and how you draw your diagrams. Anyway, yeah, electrons are negative. They're not negative energy, they're positive energy, but they're negatively charged. It's really, yeah, I'm confused too. It's okay, it happens. Yeah, but anyway, so stuff flows, electrons flow. Why do they flow? Well, I mentioned electronegativity earlier. That's one reason they flow. Another reason they flow is potential, and that thing I talked about with light, like way back, and how light works. I think that was the very first one. Electrons in valence shells can absorb energy from light, and they absorb a photon, they jump up to a higher shell, and then they release a photon, jump back to a lower shell, and they go down in energy. Sorry, there's a guy in front of me. It's like 45 degrees outside, and he's smoking, and he has a sunroof, and he's throwing his cigarettes over the top, and they're like just filling my car with smoke. Like, what the heck? Don't smoke. My grandmother smoked all her life. It's not worth it, okay? Just don't smoke. No, it's bad for your health. And if you do smoke, I mean, you know you should quit, but I know it's not easy, but there are ways to, so maybe pursue those. Don't find this offensive. I'm not judging you, it's bad for your health. Anyway, I digress. Yeah, so charge flows, negative, positive. It does that because it absorbs energy. That's one reason why electrons will move, but they'll also move when there's a potential. And what I mean by that is a potential for something of high energy to go to a lower energy. That's called voltage in terms of electricity. So something has a voltage when it has high energy electrons in it for one reason or another, or it's stuffed with electrons. That could be another reason. Because electrons, think of them, if you know how gas works, so like matter, the state of matter, gases, air we breathe in or stuff like that. It likes to flow from high concentrations to low concentrations. So if you blow up a balloon, that's a bad example because the elastic is what's actually pushing it. If you pressurize a bottle and then you let the bottle open, it will shoot a bunch of air out, or whatever's in it, it'll shoot out. If you ever do this, actually you do this as a kid, I used to do this, you take like a plastic water bottle and you puff it up as big as you can, put the lid on, and then you take it, you grab in the middle, or on the sides, and you twist it in the middle, and what that does is that reduces the volume of the water bottle, but there's still air inside. And that pressurizes it because you have a certain amount of matter in a decreasing volume. And then if you pull the cap off, it shoots the cap across the cafeteria floor. And you gotta be careful because sometimes you hit people. We used to get in trouble for it as a kid, but it's just exercising physics after all. But yeah, it's flowing. The air is flowing from high concentration to low concentration. Well, same thing with electricity and with electrons. They will flow from a higher concentration of electrons, meaning there's more of them, to a lower concentration of electrons, meaning there's less of them. So not only can stuff be energized itself, it doesn't necessarily need to be energized, it just, there needs to be more of it. So if you have matter with more electrons stuffed into it for one reason or another, then it should be able to hold. Then you will have matter that's negatively charged overall, and that will have a higher potential to dump electrons from it to something with a lower potential, something with a more positive or neutral charge. And that's where voltage comes in. So you can raise voltage in several different ways, by increasing capacity, by energizing the electrons, there's all sorts of stuff you can do it. And I don't want to get too deep into the particle physics of it, but that's what voltage is. So and they are tied together. There's voltage, there's current, which is amperage, voltage, potential, current, amperage, and then there's resistance, which are measured usually in ohms. I'm not talking about units yet, but there's resistance, which is kind of just its own thing. And then there's also power, which is just amperage over time, I believe. Or, sorry, P equals IV. Power is equal to amperage, which is current, times voltage, which is potential. That's how much power something has. But yeah, so current. Let's talk about current. Let's talk about amperage. Current is the flow of electrons. You might know that as electricity. I've kind of beat that horse to death. Current is the actual measurement of how many electrons are flowing. And you measure current in amps. That's the standard unit. And voltage is volts. Charge you can measure in coulombs. And I believe there's also farads, but I can't remember if farads is related to charge, or if it's related to power, or if it's related to current. I'm thinking it's current, but I'm not sure. There's farads as well. That's something else. That's a much smaller unit. I think that's related to charge. But amperage is the actual how many electrons are flowing through a space at a given time. That's amperage. So you can have something with very high amps of very low voltage, and that's just think of that like a city sewer line. Like it's a big wide pipe, but it's not pressurized at all. It's kind of just flowing downstream. It has a wide area. Like the water can flow, the current can flow, but it's not in any rush to get there. So that's kind of high amperage, low current, or high amperage, low voltage. You can have high voltage, low amperage. That's that's where you get like Van de Graaff generators come into play, or that's like lightning. Although lightning is a mix of both. Actually, I'll use my example for both. But you can have high voltage, low current, which is the energy really wants to escape and not be where it is. And for one reason or another, it's held there. But when it's released, it only releases a little bit of electrons. I'm trying to think of, you've probably seen like those science videos of a weird silvery ball atop a tower, and then there's like a big arc of electricity off of it. That's high voltage, low amperage, low current, which are from Van de Graaff generators, which all they do is they basically trap electrons in that silvery ball at the top, and they're using a physical motion, You ever see, like, you rub your feet on carpet if you're wearing socks and you get a static charge and then you can shock people? That's all it does. It's rubbing a piece of fabric against something that has electrons, and it's carrying those electrons along the fabric and dumping them in that silvery bell at the top. And it's trapped up there. So there's a lot of electrons, but their current is low because there's nothing forcing them out except just more of them being there, just the pressure's building. And when they leak out, they don't all leak out at once, they leak out bit by bit, and that's why you get those, like, arcs off of them, and people can touch them, and they're pretty harmless. It's Van de Graaff generators will do that. Lightning is an example of high voltage, high current. So lightning is like a giant Van de Graaff generator. It's storing up electricity in the clouds via friction, and I can get into why friction makes electricity in a bit, but it stores up a ton of charge, and thus that charge, which, by the way, let me define charge not in the positive or negative sense. That is a thing, but coulombs is a measure of how many electrons are in a space. So if current is how many are flowing through a space, it's like the difference between distance and velocity. Like, distance is, okay, how far is something? Velocity is how long is it going to take us to go this distance? How long till we get there? That's current. Maybe that's a bad example. I don't know. It makes sense in my head, but I'm an engineer. So charge is how much electrons are there. Clouds will, during a thunderstorm or something, there's a lot of movement going on, a lot of wind gusts, a lot of current, a lot of charge. Charge is being built up. There's electrons being built up. And then all of a sudden, it needs the release because it's built up so much. But unlike a Van de Graaff generator, the scale is so much larger. It's not one tiny silvery ball in the end of a tower. It's like the entire sky, which, debating on how big the sky is. Go see my video about space if you want to see how big the sky is. But we're not to hear about it. But anyway, so a lot of charge built up, and there's a lot of potential because it's just like the Van de Graaff generator. It's dumping it in, and there's nowhere for it to go until all of a sudden it ekes it out at once, and then you get a lightning strike, which is high current, high voltage, but it's only for a moment. It's not sustained, and that's because the charge dissipates very quickly. Because the sewer line, when it thunders and storms, the sewer line fills up. Same thing with clouds. When it storms, that sewer line of charge is literally the air. It just goes for it, and it all dumps at once, and that's dangerous. It's actually, electricity is dangerous in general for biological life, and I'll get into that in a sec because I want to talk about friction with it, but I'll get into that. So that's current, that's voltage, that's a little bit of charge. Power is, it's current times voltage. It's what's the potential and how much is flowing. That's your power. So it's stuff is flowing. How powerful is it flowing? That's your power. Fairly simple when you know the other two. Resistance is it's kind of talked about with insulators a bit. Resistance is the property of matter that's it's related to these things, but it's not an intrinsic property of electricity itself. It's more property of matter that's related, but not necessarily mathematically related. It is, but that's more semantics. Anyway, resistance is measured by how much, it's ohms is the unit, how resistant is this material to electricity flowing through it. And it's tied to voltage in the sense of you need this much energy to overcome this much resistance. And if you have voltages under a certain level of resistance, then your energy can't flow. But once you go over that, it can start to flow. V equals IR is the equation. voltage equals current times resistance. And you can rearrange that. It's an equation. And that is the basics of the math of electricity. I guess I'll get now into practical applications. Woo! So yeah, electricity, it can kill you. How it kills you, though, is interesting. So I mentioned in the last pep talk about sleep that our brains are wired and have constant electrical signals going through them. Well, electricity can disrupt that. I mean, there's electricity going through your brain, but when you dump in more than it's normally used to, it can disrupt that. And when it's disrupted, it causes issues. And you can probably imagine what dumping electricity through a super complicated biological tissue that is soft does to it. It throws it out of whack. But you can also, some stuff, like our skin, doesn't conduct electricity as much as, say, like aluminum. Aluminum's a bad example. Let's say copper. Copper's a pretty good conductor. Silver's the best conductor. Silver is the measurement by how resistance is calculated, I believe. And you can, it's weird because you can get in the superconductors, which are more conductive than silver, I believe, as well. But silver is the non-metamaterial standard of elements for conductivity. Like silver has zero resistance over a certain distance or something, and it's very close to zero. Everything has some resistance, but silver is pretty low. It's the practical lowest one. So we'll talk about silver. So silver has a lower resistance than your skin. So if you have a wire and let's say you're wearing a silver ring. I'm wearing a silver ring right now. My class ring is made of silver. If I have a wire and I attach it to both sides of my ring on either ends, the shortest path for the electricity to go would be to go through my finger. But the least resistive path is for it to go around my finger and go through the ring, because it's made of silver. So electricity, if you know how it flows and you know what you're dealing with, you can be safe. Resistance is key. That's why if you're ever doing electrical work, you need to have high resistance gear and equipment that you wear, so that electricity doesn't flow into you. That if it even were to touch you, the potential's too low because your resistance is so high. That's what I mean by that. Alright, I'm trying to think. I'm trying to remember what exit I'm on. I'm on 695. There's Ellicott City. There's Baltimore. Where's the 95 exit? I don't normally come back this way. I'm going the back way, which is really just the Beltway. Anyway. So, yeah. Electricity flows practically. Now friction. Let's talk about friction of electricity. Stuff gets rid of its electrons when it rubs up against other stuff. Static charge on a carpet, Van de Graaff generators, lightning bolts, and that's why when electricity flows through something, it gives off heat. Typically, it actually always, it's radiating heat. Because you have these electrons that have a higher energy level or higher energy state, and they're flowing and they're moving, and anytime something's moving, it's moving against something else, and there's forces that of that atom that want to hold on to the electron, but the electron has more energy than those forces at that state, and it's jumping from one to the other. Now that battle of energy causes friction, and friction generates heat. And I don't want to have to explain friction. Just know that friction generates heat. We'll leave it at that for now. And so if electricity goes through you, you have a higher resistance than a lot of things. But if it still flows through you, if it has enough potential, because your resistance is high as a person, your tissue, it's going to generate a lot of heat. So when you are being shocked by something that's actually powerful, not like a children's toy, it disrupts your biology and how your cells communicate with one another, but it also heats you up. And if it's intense enough, it will burn you. Electrical burns are no joke. They're not fun. So you got to be mindful of that. That's temperature, and that's friction for you. Now there's some things, that's also why wires get hot too, by the way. Hey, there's the 95 exit, cool, 2 miles. I'm not lost, I was starting to get worried for a second. But yeah, so electricity. Now how is it practical? How do we actually use electricity to do things? Because you've probably seen electric cars run on electricity, your alarm clock does, your phone that is an alarm clock does, just about everything runs on electricity in the modern era. And you might ask yourself, well, how does that happen? Well, electricity has power associated with it, like I mentioned. And you can actually harvest that power by influencing the potential of it. Because you can move something. Like, it's like it's like hitting a baseball. You hit a baseball, and the baseball moves, right? That's the same thing with electricity. You're hitting, or you're making electricity move in some way, and that has energy associated with it. And that energy can do things. It's useful work if you know how to harness it right. So stuff like motors, for example, electric motors, super useful, super useful. We use them for everything. That's how we generate electricity for the most part. That's how we use it to do practical things. That's how electric cars work. That's how dams generate power. That's how your clock on the wall works, assuming it's not digital. It's motion being generated from electricity. And I don't want to explain how motors work. They're pretty cool though, but they use electromagnetic forces. So there's a tie between magnetism and electricity, and that is a very complicated subject. But for all intents and purposes, electricity and magnetism go hand in hand and can generate work and do things together. That's how that works. So motors use this mechanism to make stuff move. You put electricity through it, and well, it attracts the magnet that's inside of it, and the magnet then moves. And when the magnet moves, the shaft that's attached to the magnet moves. And then you turn the electricity off and it rests again. Then you turn it on in another spot, and then that makes it move again. And you do that fast enough, and you get circular movement smoothly. And that's how motors work. Same is true in reverse, because there's a tie between electricity and magnetism. If you move the motor, if you move the magnet without electricity being applied, it will generate electricity. It'll generate electrons flowing. It'll induce a current is the word there. Induce, like you're inducing someone to be born. I guess you induce the mother. But anyway, you induce electricity. You drop an induce on it, and it flows. And you might be thinking, well, what about that matter's going to run out of charge? Well, no, not true. Because for electricity to flow in most circumstances, you need a full circuit, is what it's called. You need a circular connection. So an exception to this is like a lightning bolt, like it's a one and done, like it's gone, because you're going from a high potential to a low potential very quickly out of the fire hose, or it's like depressurizing a bottle of air, like I mentioned earlier. That it doesn't necessarily need a circuit, it just needs a high potential and a low potential, which you could argue is a circuit. But what I mean is I guess the air does return back to it. Either way, that's like a one and done shotgun type thing. A circuit is a flow. It's a constant flow. So stuff will go from a higher power or higher potential to a lower potential. It'll do work, but then it'll return to the thing that makes it a high potential, and it'll keep going. So if you have, let's say, a dam generating power via water going over a motor, spinning the motor, electrons in that entire circuit, the circuit is made of matter, and that matter has electrons in it. The electrons are moving, and they go from a high potential to go do some work over across your power lines in your house and run your Nintendo Switch while you play Animal Crossing. And then once that they've lit up the screen and they've taken all your sensor inputs, that electricity flows back down, or the electrons will flow back, assuming you're plugged into the wall on the dock, will flow back to the circuit breaker. It'll flow through your house, it'll flow back through the power lines, and it'll flow all the way back to the dam, and it'll return at a very low energy state compared to when it left, thus completing the circuit. Now, you might be asking, well, what happens if you take your Switch off the dock? How does it work then? There's no circuit. And, well, there's circuits in your Switch. But that's how batteries work. Batteries are like the lightning bolt, or like the puff of air, except it's controlled and it's slower release, ideally. They store electrons at a high potential state, and then release them at a set rate. And you can vary that rate too with modern electronics, but they release them at a set voltage and at a set current, which means a set power. It's P equals IV, and I is current, V is voltage, P is power. So batteries will store up electrons of a higher energy level, use them for work, and then those electrons will return back to the battery at a lower energy level. You're not losing electrons. No matter is created or destroyed, it just changes form. And matter and energy are tied hand in hand, so it's that, I guess. But yeah, it changes form. That's the main mechanism of how batteries work. So, you've learned how to make electrons a higher potential, by shoving more of them, or by moving them somewhere, or just moving them, and that's one way to do it. Now let's talk about why metals in particular make such good conductors of electricity. So, metals are interesting. So there's ionic bonds, there's covalent bonds. I'm going way back to the start. And then there's one more bond called metallic bonds. So metallic bonds are interesting, where ionic bonds are usually one or two atoms or a couple of compounds that are charged and they react together and you make polymers and all sorts of weird other stuff. Ionic bonds are cool. Table salt, ionic bond, I believe. That's sodium chloride. Chlorine has a pretty high electronegativity, like fluorine, and sodium has, I'm trying to remember if it has one or two valence shell electrons, meaning the outer shell. So it's more eager to get rid of its electron. It's easy, has a low electronegativity. So they come together. Covalent bonds, they share. It's one electron, but it's shared by both atoms. Instead of one's taking from the other, they decide to hold hands. And then there's metallic bonds. So metallic bonds are interesting in that they, I don't want to say this wrong, but their outer valence shell, they don't hold on to very tightly at all. Like, regardless of if there's other matter next to it or not. Like, the bonds that you get there, because the attraction forces are depending on distance, the outer electrons that are orbiting metallic atoms usually have a larger distance than most other atoms. Not necessarily. I mean, you go down the rows and you fill the shells, but metallic stuff usually has electrons in the D and F groups. And I know I'm saying usually, it's because I don't have a periodic table in front of me. I could tell you exactly where it is. There's like a weird, you've probably seen this and always wonder what it is. There's like a line that typically is on the right side of the periodic table. It's like a zigzag line. It looks like stairs almost. And that is to separate the shells. Watch a video on how the periodic table is developed. It's actually pretty cool. And complicated and had a lot of iterations. And I'm glad we ended up with what we did today. It makes it a lot easier to read. But anyway, so stuff in the middle has electrons in the D shell and the F shell, which are pretty far from the nucleus and aren't held on to as tightly. So metallic bonds, they utilize this where it's kind of like an ionic bond and it's kind of like a covalent bond, but it's not either. They're sharing electrons, but they're also at the same time stealing them, making them positive and negative respectively, and which brings them together. But they're also sharing them. But they don't really care enough to do both at the same, or both independently of another. Like it's like an assembly line. They kind of just pass one to the other. So you get this thing called metallic bonds where the electrons are able to flow very easily in the outer shells of these high atomic number atoms. And some low atomic number atoms too, but because you get into superconductors, and those are usually made of nonmetals or metalloids, or you got semiconductors like silicon is a great semiconductor. I believe it has 4 valence electrons, so it's right in the middle of I want some, but I also have some, and I don't need more. So you have metallic bonds. They share their electrons easily, and because of that, they make great conductors. They're able to flow electrons quickly and easily, and because they're able to flow easily, you're able to have current through them easily, and that's why wiring is made out of metal. That's why lightning rods are made out of metal, because the lightning has low resistance when it goes through the metal. Metals have typically low resistance for this reason. And so metallic bonds are good for that. Okay, so that's practical. What else? You might be asking yourself, well, how do we get electricity to do all the crazy stuff we do? You explained motors, but you didn't explain anything else. Well, that's your good point. Modern electronics are complicated, and I could explain the basics of electronics, but you probably won't ever run into that in your daily life unless you're an engineer or you need to replace like a fuse in your car or something. But even then, that's just a YouTube tutorial. You don't need this podcast to learn how to replace a fuse in your car. So I'm not going to explain electronics per se, but just know that this electricity, this power that can do work, can also influence the states of things. But we'll call it state, because you have state-based electronics. So your computer, your CPU, is a dumb box of switches, as my old professor used to say. Brilliant guy, PhD, master's and bachelor's degree from MIT. And he'd start every class pretty much with, computers are a dumb box of switches. What we have now, like our screens, are just some candy-colored Victorian era. He had like an analogy where he was comparing computers to like Victorian era desks, which are these very elaborate desks with all these drawers and sub-drawers and subdivisions in them. And that's how modern computers are. They're a bunch of just candy-colored, coded, digital mess. But computers back in his day, he actually built the servers for MIT back in the, I want to say, oh man, how old is he? I can't remember if he said it was the 90s or the 80s. but he built MIT servers for a couple of years and maintained them. Brilliant guy, like I said. Dr. Sander, Robert Sander, if you ever want to look him up. He's done a lot. He teaches at University of Maryland currently. Anyway, he was saying that computers are dumb box of switches. What I mean by that is they are on or they are off, and they're able to hold that data and hold that state of, can they be on, and if you flick them on, they stay on, or if you turn them off, they stay off. And that's solid state memory is built on that principle. But you can use electricity to influence the state of these switches, to turn them on or turn them off. And that's basically how computers do anything, is they just make decisions based on, is this thing on, is this thing off, and measure it. You've probably seen binary before, just ones and zeros. 1 is on, 0 is off. Computers work in binary. They work in, is this thing on, is this thing off? And they have enough technology that they can interpret that data. I don't want to bore you, but if you have a 0 in binary, it's 0. If you have a 1 in binary, it's 1. If you have a 1, 0 in binary, you suddenly have 2. If you have a 1, 1 in binary, it's a 3. Like, that's how computers are able to interpret that data and use it to do things. That's where you get floating point errors and checksum errors, and I'm not getting into that. Anyway, electricity is used to power logic gates and switches, and that's how electronics work, that have memory. Electronics that don't have memory, you're thinking like resistors, transistors. Well, no, transistors have memory somewhat, if they're state-based. Your power sources, a light bulb, which light bulbs work, by the way, through that friction concept I explained earlier, of you're passing electricity through this wire. That wire's getting really hot, and like 97% of the energy going through that wire is converted into heat, but like 3% of it is turning into light, visible light, for incandescent light bulbs. Off of the concept that I explained in the very first pep talk of light and how it works, those electrons are absorbing energy and they're up to a higher state. So sometimes they just straight up emit photons to get to a lower state, but most of the time they're emitting, well, hold on, wrong. Heat, when it's generated from a light bulb, when it's radiated out that way. Sorry. Oh man, that's hard to explain. So the wire itself heats up, but not from radiation, for friction. But the wire is also able to radiate heat off of it in the infrared spectrum, as well as through convection of just the wire touching the casing and the glass and stuff, and the partial vacuum inside it. But the most of that energy is converted to heat and incandescent. The rest goes as light, visible light, that is, we can see. Yeah. LEDs are cool. LEDs are different. They're light emitting diodes. LED, light emitting diodes. They work not like incandescent light bulbs. They have I don't want to just hand wave and say electronics, but there's a it's not a phototransistor, that's something else. It's a diode. If you don't know what a diode is, it's a, how do I explain basic electronics from the ground up? It's a something that electricity can flow through and it does something. That's a bad definition. A diode is a piece of electronic hardware where electricity can flow through it in one direction, and when it flows through it in that direction, it does something. So transistors are similar to diodes, in that they have electricity flow through them, but they're more granular in their settings. Like Diodes don't ever allow electricity to flow back through them unless you overcome the diode's resistance, in which case you burn out the diode permanently, usually. Transistors, it's a little bit more nuanced. Anyway, so a light-emitting diode, when you put electricity through it, it's covered in a chemical, it's covered in a chemical that when electricity is flowing through that chemical, it gives off light. It absorbs that electricity's potential energy, it excites the electrons go to a higher shell instead of flowing, and then those electrons emit photons, and you get light. And then the electrons, when they go to a lower shell, because there's more electrons coming in, they're pushed, and they flow out of the diode, the light-emitting diode, thus completing the circuit. That's LEDs. Now, interestingly enough, the last LED color to be made was white. They made every other color before white, because to make white light is every color of visible light at the same time. And it depends if you're in color theory or if you're in physics. I'm not going to explain the nuances. But in color theory, white is the absence of all colors, and black is all colors put together. In physics, white is all colors put together, and black is the absence of all colors. So that's the difference between color theory and physics. If only artists and engineers could agree. Artists and engineers can agree. If only artists and physicists could agree. That would make things a lot simpler. But anyway, in physics, because we're not in art right now, in physics, they were coming up with these compounds that they could run electricity through to make colors, and they emit wavelengths. I talked about gamma ray spectroscopy a while back. It's similar, but it's not gamma rays. But the compounds are emitting photons in certain bands, certain colors, certain wavelengths. And because of that, they kept trying a bunch of different compounds, and they could get different colors. You know, a red LED is different than a green LED. Because it's a different metal it's a different compound on the LED that electricity is going through to make that photon, that wavelength. The last one they made before, because you need all the colors to make white, all the colors minus one was actually blue. Blue wasn't invented till, I believe, the 90s, or is there 1989 or like 1996? I can't remember. I remember learning about it when I taught high schoolers electronics my freshman year in college. It was fun. But I digress on that. Blue was the last color made because they just took a while to figure out a compound that made blue light. What can I say? It's that simple. That's a practical application. What else? Because I'm running out of fumes here. I'm actually pretty tired. I'm on maybe 6.5 hours of sleep, maybe 7, which is fine. But if you remember my sleep talk, I recorded that yesterday. I was on 5 hours of sleep, and I'm driving, and I've been driving for a while, and I've been talking for a while, so my brain hasn't had as much oxygen because it's going through my vocal cords and my lungs, so it's making me tired talking, and driving is a bit tedious, and thinking is burning up energy in my brain. And so, recording these podcasts make me tired. But that's because of the physiology of my body. I am motivated and highly energized as a person to do this for you. I hope you enjoy. Electricity. Talked about batteries, talked about motors, talked about how you store it, talked about how you use it, talked about what it is in physics, talked about how you move it. What am I missing with electricity? I could talk about its relation to magnetism, but that's very complicated. All you need to know is that magnetic forces and electrical forces, when they are perpendicular to each other, cause the other one to move. So, current going through a wire naturally generates a magnetic field around that wire in a perpendicular circular pattern. And to know what I mean by that, you kind of need to know the right hand rule. So in engineering and physics and literally everything that uses dimensions, there's something called the right hand rule. So if you have a right hand, take your right hand. If you don't have a right hand, I'm sorry. Think about your old right hand. Or if you never had one, I'm sorry you were born that way. But look at someone who has a right hand and hold it up. Just hold it with your palm facing you. Alright, cool. Now turn it sideways so that your pinky is in line with the ground. It's parallel with the ground. But your palm's still facing you, right? Your thumb is out, your thumb is pointing straight up. Have your thumb point straight up. Good. Now, make sure your pointer finger is perpendicular to your thumb, 90 degrees. It's pointing out. Good. Ooh, I need to stop at IKEA to pick up my brother's Christmas gift. I'm getting him a walk. Sorry, I'm about to pass by IKEA, I just remembered. I need to do that. But yeah, you take your thumb, your pointer finger are perpendicular to each other, and take your middle finger and pull it in close to you, like pointing at you, 90 degrees from your pointer finger and 90 degrees from your thumb. That is called the right hand rule. So your axes, your coordinates are determined by this, and if you really want to, move your wrist outward so that you're doing like a finger gun, but just keep your middle finger out, away from your palm. That's the right hand rule. So when I say something's perpendicular, I mean it in that sense of like, if something is flowing in the direction of my thumb, then perpendicular to my thumb is both my pointer and my middle finger, but you go in order of thumb to pointer to middle finger back to thumb for the flow. So if you have electricity flowing in the direction of your thumb, the magnetic field is going to be generated in the direction of your pointer finger. Yes, I think so. Yeah, and then you rotate around the axis of your thumb. So that's it's like, you remember, I don't know if you've ever seen this, maybe you used this as a kid, one of those old compasses, not a magnetic compass, but a compass that it has like a point you put somewhere on a table, and then it has a holder for a pencil, and then you move it around that point and you can make perfect circles that way, or near perfect circles. You're kind of doing that with your pointer finger and your thumb. Your thumb is pointing up, but your hand's moving around your thumb, and it curls in towards you because of the right hand rule, and that's the direction that the axis is. So it curls towards your pointer, or curls towards your middle finger in the direction of your pointer finger, around your thumb. So that might have been a bit complicated if you've never been explained the right hand rule before, but that's our standard for direction for just about everything. And if you ever study engineering, you'll see that everywhere. Your axes are all determined that way as well. Alright, where is this IKEA? It's been a hot minute since I've been here. Hope they're open. Should be. It's only 4:47. I hope I don't have to go far. Once you go into an IKEA, you can't ever really get out. There's a SCP about the Endless IKEA. That's a fun one. Highly recommend reading it. But anyway, yeah, you go into an IKEA and you have to go through the entire IKEA to get to the exit. Because that's how they're designed. They're brilliantly designed that way, so that you have to see the entire store before you can leave. It's so clever. Give it to the Swedes on that one. They figured out something brilliant. But anyway, because I'm almost at IKEA, I need to wrap up this conversation. Just made it through the light. Cool. About electricity. It's also starting to get dark, so lights are going to turn on. Electricity is going to be used. Because we have electricity, we are able to operate in the dark, unlike most of human history. Which, I guess we had lamps, right? And lamps usually burned oil to give off light, because fire gives off visible light. But now we don't need fires. We we can use electricity, and it's a lot easier to store electricity than it is to store fire, because you really can't. It's a chemical reaction. You can store things that have potential to burn, just like how you can store electricity in things that have potential, but alas, you can't really store fire because it's a actually chemical reaction. Fun fact, fire is hollow. I might explain that at a future point. But what you see as fire, it's hollow. Anyway, with that, I'm going to end this pep talk. Thank you for listening. I know I got a little bit pedantic towards the end. Forgive me for that. But I hope you enjoyed. And if you didn't enjoy it, you should have stopped listening a while ago. But yeah, so have a wonderful Wednesday. And go hug someone, because hugs are nice. Bye.